So welcome to the last lecture. And so today let's go for the summit. Let's do the primordial spectrum for the fluctuations which are produced by inflation. So let me just briefly recapitulate what we have done yesterday. So we basically, well, we are training a lot. We went first to the base camp and then to the second camp and so on. But one approximation which we used was this approximation of test massless scalar field, which doesn't backreact on the geometry, but simply solving and quantizing a scalar field, which is in the background of FRW space. And so the action, when written in the conformal time and written in the Mukhanov's variable, it reads like this. And I showed you that if you are interested in the power spectrum, which is like a two-point function in the k-space, coming from quantizing this action, you get a prescription that is equal to absolute value fk square divided by the scale factor square, where this function fk is a function of eta of our conformal time and satisfies this differential equation, which is called Mukhanov's equation. So of course, in order to solve this equation and plug it here so that you get the power spectrum, all you need to do is you need to provide the right conditions to solve this equation. And so usually people impose this Bunch-Davis vacuum. And so that leads to an initial condition for my fk, that fk behaves like that the frequency of my oscillator is actually constant. This guy vanishes, and it's just e to the I k eta. Okay? And this is an initial condition which is true before the inflation started, so at very, very early times. We also calculated a solution of this equation if you have de Sitter space. So if the inflation is completely de Sitter space, it cannot be, but it can almost be a de Sitter space, then you can actually calculate this thing exactly, and the function reads like something, but at late times, meaning so when the inflation is finished, so at eta equal to 0, your fk square looks like 2k cube eta square. So now if you plug whatever the a square is, it cancels your eta square, and what remains is this 1 over k cube power spectrum, which is the scale invariant power spectrum which you get. And it's the famous result for de Sitter space. Okay, so this is for fixed gravitational background. So the last step, and the most difficult calculation, is now to take the backreaction into account. And so now we'll be studying a couple of perturbations, gravitational plus scalar perturbations. So that's the last step. So actual calculation. So let's get the summit of our Mount Everest. And so for that is this whole chapter in Weinberg basically dealing with something which is called cosmological perturbation theory. Which I will just briefly mention in like 5 minutes, and then you will spend lots of time doing it actually in explorations. So if you want to see all the details about the cosmological perturbation theory, take the exploration course. So what we are doing is that we are taking our action, which is again, let's put m Planck square instead of 1 over g Newton, d for x, square root of minus g, and then 1/2 r minus 1/2 d phi square, and then we allow for a potential of phi as well. And the idea is to take FRW as background. So we'll be taking this k equal to 0 as we did above. So your spatial part is just the Euclidean metric, and study the couple of perturbations. And the perturbations are, so we go from g mu nu G mu nu plus H mu nu, which is a perturbation of the metric. And then we also have a perturbation of the field. So we have some background field phi, and the perturbation is var phi. Okay, and so this will be coupled, and so it's quite nasty business to deal with these. So now what we want to do is we want to calculate this power spectrum, and so for that, in order to calculate the power spectrum, you need basically something which is quadratic in your fluctuations, right? So it's a two-point function, so we need quadratic function. So you need to expand your action into quadratic order in the perturbations. In fact, actually probably into even higher order. Okay, so need to expand S to second order. And of course, the complication is the gauge fixing, right? Complication is the gauge. So you know that your pure gravity has this diffeomorphism gauge freedom. So I can always change my coordinates if you want. But in the end, if you have just pure gravity, all you have is just 2 degrees of freedom describing your graviton. Okay, so now we have a gravitational theory coupled to a scalar. So what you expect is that in the end, you have 3 degrees of freedom, 2 describing your gravity and 1 describing your scalar. However, you can sort of, transfer these degrees of freedom from the fields to gravity and so on. So it's actually not really, obvious a priori where these 3 degrees of freedom are hiding. So you can definitely prescribe a gauge where, for example, you say, my scale field doesn't exist. So it's like the fluctuations of the scale field are just, and I just redefine and absorb this into, let's say, time, right? And so I prescribe a surface where I have no fluctuations of the field, but everything will be, described in this t coordinate. So to extract the true degrees of freedom is relatively elaborate calculation, and it's done in your homework. So if you are interested, look to your homework. Also in explorations course, it will be discussed in offensive Hamiltonian formalism. Okay, so need to, complication is the gauge, so need to gauge fixed. Fix, and so we need 3 degrees of freedom in the end. And as I said, this is in homework discussed. So now convenient tool, which is basically the tool of this cosmological perturbation theory, is to use again this SVT decomposition, which we already used for when we discussed the CMB, the polarization of CMB. So use as scalar vector tensor decomposition. So if I write it again, so you split your metric, your perturbation of the metric, into H00 is phi, and then H0I is A times VI plus DIV. Okay, where again, so we are basically splitting into scalars and vectors and tensors. But always your vectors are transverse. So they have only d-1 components. And if you have tensors left, they are transverse and traceless. So they have less components. So here, this is just a scalar. This is like a vector, so I'm splitting to a vector which is transverse, so d-1 components and the scalar. So that gives me d components of this thing. And finally, your Hij, which is the formula which we use for CMB. So we put a square. Now, Gij, which is the transverse and traceless thing, and then plus 2 di dj. So wj is another vector which is transverse, and then a scalar di dj chi, and then the trace and that's the zeta, which I don't know how to write, delta ij. Okay, so that's your decomposition. As I said, you know, the vectors are always transfer, and gamma ij is transverse and traceless. Okay, so now what is beautiful about this SVT decomposition is that if you plug it into the action, your action actually decomposes on three different parts: on the scale part, on the vector part, and on the tensor part. And they are completely decoupled. So because of these transverse conditions and traceless conditions, they never scales never couple to vectors, and vectors never couple to tensors, and so on. So it's beautiful. So it's really, you know, that's why you're doing this decomposition, so that everything splits into the scale part, into the vector part, and into the tensor part, and you can treat them separately. Okay. Sorry?
You use the partial derivatives in this one because it's already a perturbation. Is that the reason, or because usually I think we use the variant derivatives?
Well, good point. Well, here I'm using Euclidean space, and it's probably perturbation, so I can do it this way. If you want to put a covariant derivative, it's probably the same thing. Probably the same thing. Thank you. But yeah, I think here it's probably true this way. But let me check that. So then the action splits into S and V and T, and they are, you know, separate. They are not coupled to each other. Parts. Okay, so now this was just a decomposition. We haven't chosen any gauge yet. So now it's time to, once you have the decomposition, once you have written your action into these three parts, you can choose the gauge. Okay, and so what is quite convenient to discuss these primordial perturbations is so-called comoving gauge. Comoving gauge. Or stupid letter zeta gauge. I'll have to practice writing that letter. Anyway, and so that gauge is precisely what I was telling you, is that you say that the scalar has no fluctuations. Has no fluctuations, which means that this phi equals to 0. Okay, and so you can show. So that's basically like a definition of your thing. But of course, that's not the only thing which I'm gauge fixing. I'm gauge fixing many other things. But in the end, I have to have 3 degrees of freedom, and the gauge is chosen such that the this stupid letter that is your true degrees of degree of freedom. So true degrees of freedom, or remaining degrees of freedom, the 3 degrees of freedom, are captured by gamma ij and and zeta. Okay, so now, of course, so gamma ij is a 3×3 matrix, and it's transverse and it's traceless. So in the end, it has only 2 degrees of freedom, and zeta is something like a scalar. So that's my 3rd degree of freedom. Okay, so to get here, okay, so very good. So then I told you that the actions actually split for tensors and for scalars are different, so completely decoupled, and you can show that for the tensor, the action is just m Planck square over 8 and d4 of x a cube gamma ij dot square, and then 1 over a square nabla square gamma ij. Sorry. Gamma ij nabla square gamma ij. So that's the action for the tensor, and then the action for the scalar is m Planck square integral t4x a cube epsilon, and then whatever you would assume. So 1 over a square, this thing here. Okay, so that's the result. And of course, it takes several pages to get here, right? But in the end, the result is so beautiful, right? So we have decoupled tensor and scalar perturbations, and they satisfy these very, very simple actions. Okay, so that's really beautiful and captures all the degrees of freedom which we have. So now, if you look at the action for gamma and the action for zeta, there is one important difference. Well, of course, this is a tensor, but also the main difference is this epsilon standing here. So the epsilon is the parameter which you already know. It's the slow roll parameter. Okay, so epsilon is just 1/2 phi dot square. So our background scalar field phi dot, and then m Planck square h square, or if you want, it's minus h dot over h square is the slow roll parameter. Okay, and so really that comes out of the calculation that this epsilon is there for the scalar modes, but it's not there for the tensor modes. And so this is basically the origin why the tensor modes are suppressed. So you know that this is a slow roll parameter, so it must be very, very small. It's much, much smaller than 1, this parameter. And as we will see, this is what suppresses the gravitational waves with respect to the scalar things which we get out of that. Okay, so tensors are suppressed. And I will show this to you in a minute. Okay, so now let's discuss the scalars first, and then let's discuss the gravitational waves, and then let's compare the results. Okay, so first, scalars. So that is your action. So now again, you want to canonically normalize your action so that you have 1/2 and something which you phi dot square or something like that. So again, introduce the Mukhanov variable, and this will be given by nu equals to z times. So finally, I get rid of this letter. Okay, where z has to be chosen to be 2a square m Planck square and epsilon. So if you choose this thing, then your action is just, and then you also switch to, I think this is not in conformal time. Yeah, so that's in normal time. So if you switch to conformal time again, so then you get d3x, d eta, 1/2, surprise, surprise, nu prime square, nu double square nu, plus z double prime over z nu square. Okay, so if you do that, this is what you get. And we immediately recognize whatever we had and studied yesterday, right? So this is precisely the same action which we now have to quantize as we did yesterday for the massless scalar field. Okay, so we immediately can write down what the power spectrum is. So from here, and using the results, then you know that power spectrum is just fk square divided. Now if you compare, the only difference is that we have z here and we had a there. So now we have z square here. So that's our power spectrum, where this fk satisfies, again, the Mukhanov equation with a replaced by z. So we have, again, fk prime plus k square plus z double prime over z, fk equals to 0. Now again, you impose the same Bunch-Davies vacuum in the past. And so you know what is the initial condition for Fk, and it's exactly the same initial condition as we have over there. Okay, so now so you know the solution of this guy, so you just have to plug it here, right? So the problem is that, of course, this epsilon is not really a constant, right? So this epsilon is a parameter which is much more than 1, but it's not a constant. So in some sense, evaluating these things is a little bit more difficult because you don't know what that epsilon is. But you can say that you are very, very close to de Sitter for most of the part of inflation. So you take, usually people take, so approximation, which is the slower of approximation, and then you say that for most of the part, our inflation was like having de Sitter space. Okay, so we take de Sitter. Okay, so then you know that at late times, your Fk behaves as whatever I told you over there. So approximately 1 over 2k cubed eta square. If you had de Sitter, then your scale factor behaves, that's what we discussed yesterday, 1 over eta square h square. Just look it up into in your notes. And then our power spectrum is just this Fk square over z square, not over a square, but over z square. But z square is this guy here, sorry. So there's z square here. Okay, so this is z square, so it contains a square. I know what a square is, and I know what this guy is. So putting everything together, you know that P of zeta k is 1 over 4 k cubed h square m Planck square and then epsilon. Okay, and so this is evaluated at the time. So we are interested in this primordial fluctuations, which is eventually transferred to your plasma. So this is evaluated at the time when your mode leaves the horizon, when actually the mode crosses the horizon and the horizon is becoming bigger. Okay, so at the time the mode freezes and this power spectrum is preserved. Okay, so you evaluate it at t equal to t star, where this t star happens when the wave mode, well, when k of that mode equals to the horizon, which is h time a. Okay, so that's your condition. And this is your spectrum. Okay, so that's a beautiful result. So now you see k cubed here. Okay, so it almost looks like you have a scale invariant spectrum. Well, you have this epsilon here. But also, if you notice, then for different case, t is different, because as you have this picture, this is your horizon, and this k enters here, this k enters here, so this is my time. So this mode enters at one time, this mode enters at later time. So bigger k, later time it enters, right? So this thing basically means that you don't have scale invariant spectrum, because different modes enter the horizon in different times. Okay, so spectrum is almost scale invariant, but different modes enter at different times. Okay. Okay, so that's the power spectrum. I told you that one parameter which describes our universe is this spectral index. So let us calculate what the spectral index is for the scale waves. Okay, so for that, let me just remind you, we have these, we will express this spectral index in terms, okay, so we want the spectral index. But we will express it in terms of these slow roll parameters. So you'll express it in terms of epsilon. I just remind you this is h dot over h square. And then the other slow roll parameter was eta. Well, eta is our conformal time. So let's put, I don't know, eta tilde or something like that. Just saying that this is a slow roll parameter, not conformal time. And this was defined to be epsilon dot over h epsilon. And these two parameters, when they were much smaller than 1, so the first one told you I have actually an inflation, so my commuting radius is decreasing like crazy, and the other one tells you that this lasts sufficiently long. Okay, so we have these two parameters. And so let's differentiate that condition which we have when the horizon actually enters the, when the mode enters the horizon. Okay, so we have a condition that k equals to HA, and then let's differentiate this condition with respect to k. Okay, so what we'll be doing is d over dk. So we have 1. Okay, so now h depends on t, and t depends on k. Okay, so if we want to differentiate h, we have dh over dt and dt over dk times a. And then we have h plus dA over dt, dt over dk. Okay, so this is what it is. So this is h dot. And this guy is a dot. So now I put a here, and then I return it back. Okay, so I will have a dot over a is just another h, right? So I have that this is equal to dt over dk, and then I have h dot a, and then plus h square a. Okay. Very good. So far, very easy. So I can express what dt over dk is, right? I just divide by this thing on the other side. But let me also multiply it by k. So let's write what k times dt over dk is. Well, k is HA. So this is HA. And then divided by whatever this thing is here. So it's H dot A plus H square A. Okay. So now you can divide by HA numerator and denominator, and what you get, and so you see you are getting something like h dot over, so now if I put h, well, over h squared, so there must be epsilon showing up at some point. Okay, so if you do it, what you find that this is equal to 1 over h, 1 minus epsilon. Okay, the most complicated calculation which we are going to do today is just happily over. So just remember this is k dt over dk. And it's just a differentiation of this condition. No more complicated calculations today. Okay. So now we want to express this spectral index in terms of these things. So definition. So if you remember, the spectral index was equal to 1 plus, and then k, well, this is equal to k d over dk logarithm of k cube and p theta k. Okay, so ns was 1 plus this thing here. That was the definition I gave you yesterday. Okay, so now you can write k d over dk as k dt over dk d over dt. Okay, so this is equal to, and then for k dt over dk, I can use this expression here. So I have 1 over h 1 minus epsilon d over dt, and then this logarithm. And then I can use the power spectrum which we calculated over there. So there you see I have 1 over 4 k cubed, so k cubed cancels. And I have h squared over 4 m Planck square and epsilon. So far, we happy? Okay. So now, well, here, I want to differentiate this guy with respect to t. So the only thing which depends on t is h and epsilon, and these are just constants, right? So I don't care about those constants. So let me just differentiate whatever I have. So this is 1 over h, 1 minus epsilon, and then differentiating logarithm, I get 1 over that, which is epsilon over h squared. And then d over dt, h squared over epsilon. And then you have to really differentiate this guy, which has 2 terms. So let me do it. So this is equal to 1 minus epsilon. Epsilon h squared, and now a horrible thing. So it's 2h h dot divided by epsilon minus h squared epsilon square epsilon dot. This is what it is. And then if you collect the terms, what you find out is that this is equal to, and you use the definition of your epsilon and of your eta tilde. So you see that I have epsilon dot, so this thing will become something like eta tilde. And then I have h dot, which will become something like epsilon, right? So if you do it, you get this is minus 2 epsilon plus eta tilde divided by 1 minus epsilon. Okay. So now, of course, I treat these parameters as small, so I just expand to the first order. So I neglect this epsilon in the denominator. And this is equal to minus 2 epsilon minus eta tilde. Okay, I should have said that. There is one more parameter, delta, right? And so this delta parameter, I should have said that. Now it's too late. So you can also write this eta as some, and that's what we did, a few lectures back. We said that this is equal to 2 epsilon minus delta. So that gives another slow roll parameter, which is also small. Okay, so you can write eta tilde in terms of delta, and that's what people usually use and write here. So if I put instead of eta tilde this delta, what you get out of this is minus 4 epsilon plus 2 delta, and this is ns minus 1. This is a very famous result. Okay, so it tells you that the spectral index cannot be equal to 1. And the difference, why it's not equal to 1, is exactly these slow roll parameters. So if these slow roll parameters are non-trivial, and they have to be, if your inflation is supposed to end at some point, you have to have these slow roll parameters non-trivial. Okay, and so it really tells you that the spectral index cannot be 1, and you cannot have exactly the scale invariant spectrum. Okay, very, very famous result. Questions? how much time I have? 20 minutes. So maybe I'll just only very, very briefly mention the gravity waves, because they are, after all, in your homework. So you can do it yourself. So for gravity waves, well, you would do exactly the same calculation. So we have the action, which is still written in terms of these gamma ij. So again, you introduce a Mugano variable. So you introduce mu ij equals to z gamma ij. And then this z square now will be different, and it will have not that factor epsilon there, a square m Planck square. Okay, if you do this, you again transform the action into that form which is up there. Now the only difference is that now you have nu ij, but it's exactly the same action. So again, you know what is your power spectrum in some sense, and you can calculate it. So going through all the steps as we have done for scale waves, and you will do it in your homework in more detail, you find that in the same way, the p gamma is actually, again, 1 over z square fk square. And this is equal to 2h square over k cube m Planck square. And this is, again, evaluated at the time when you leave the horizon. Okay? So this is the result of the calculation, which can be done in 10 minutes, but let's not do it here. Okay? So that's the power spectrum for gravity waves. In some sense, this is for each mode. So this is a power spectrum per each mode. So sometimes people say, well, the total power spectrum might have 2 modes. So it will be twice as big. Okay? So sometimes people say, well, the whole tensor power spectrum is 2 times p gamma. 2 times p gamma. And this is because we have 2 polarizations, if you want. So now, look at how beautiful these things actually are. So if you measure this guy, or that guy, doesn't matter, then what enters this thing? So if I measure really the distribution of the power spectrum, well, this is just the k, that's what I measure. This is just a constant I know. So you can actually tell what h was at the time when the inflation ended. Okay, so by measuring the gravity wave power spectrum, I can measure h. Then you can return back to the scale spectrum. Over here, I already know h from measuring the gravity waves. So I can determine what this epsilon is, right? So the other spectrum gives you the epsilon. It gives you the epsilon, the slow roll parameter. And then, if I measure ns, I know what my delta is. So I know everything about inflation just measuring these two power spectra, right? So it's one-to-one correspondence, right? So but it tells you exactly what the right model for inflation is, what these parameters are, and so on. Okay. So now people also define the spectral index for gravity waves, but that's defined differently. So spectral index. And the difference regarding the definition for scale waves and for gravity waves is that you don't put that +1 there. So you just define nt for tensor modes. S stands for scalar, and so t stands for tensor. And you do it t over dk, and then logarithm k cube, and then pt. And you see there's no this +1. So that's the difference between tensor modes and scalar modes. And again, you can do exactly the same calculation as we have done. And if you find if you do it, you find that this is equal to minus 2 epsilon. Again, very, very powerful result. So the spectral index for the tensor modes just gives you immediately this epsilon parameter, the slow roll parameter. Okay. So now this famous ratio, tensor to scalar ratio, that's a famous quantity. So tensor slash scalar ratio, and it's called R, and it really measures, you compare the power spectrum for tensors and you compare the power spectrum for the scalar. Well, if you use the formulas, which we have over there, the only thing is the epsilon, which is different, and there's some number. Okay, so the number turns out to be 16, and the epsilon is there. So this is equal to 16 epsilon. So it tells you that the power spectrum for tensors is suppressed by this smallness of epsilon a lot. So you have, you expect much stronger signal for scalars than you expect for tensors. Okay, if epsilon is small. So this is exactly the parameter which was originally measured by BICEP, by this identifying these gravity waves coming from inflation, and they said this ratio was 0.2. So it was actually lots of tensors you got, but it went away, and it's probably smaller than 0.01. Okay, so we are not that lucky to have such strong gravity waves coming from inflation. But this is the famous ratio, so which is probably okay. So BICEP said that R is 0.2, but probably much smaller. So probably R is smaller than 0.01. It's actually the right thing. But if it is of the order of 0.01, we will know probably soon. So that's actually measured. Okay, so this is a very, very famous ratio. Something to take out from here. That's the number. Okay. So finally, this ratio, if you look at what epsilon is, well, so it's 16 epsilon, but at the same time, epsilon is related directly to your NT, to the spectral index of gravity waves. So this thing is, of course, equal to minus 8 NT. So if people can measure, the spectral index for tensor modes, and can measure independently this ratio, then this must be satisfied. And that's a non-trivial consistency check. So if this is not true, then your single field slow roll approximation for inflation is wrong. Okay, so this is a consistency check. That this equals to that is a consistency check on your model of inflation. So now, all we have done so far is that we have discussed basically like 2-point functions. So we have discussed this power spectrum, which is like a 2-point function of these fluctuations. If our probability distribution is Gaussian, then this is everything you need to know. It's a 2-point function. And everything else is given by this Wick theorem, and everything, if you have odd number of things, you will get 0 and so on. However, people consider a possibility that maybe this distribution is non-Gaussian. And then you could have non-trivial, let's say, 3-point function. Okay? And so this was first calculated, the prediction was first calculated by Maldacena. And you will do the calculation. What would be the prediction if you had non-Gaussian this probability? You will do it in explorations. But of course, that must be suppressed, right? So the 2-point function much bigger than this 3-point function because we have almost Gaussian distribution. So at this point, there is no observation indicating that you would have non-Gaussian thing, but you can speculate in theory that this is the case, and you can calculate what the 3-point function would be, and then and it will give you something to measure in the future. But you will do this calculation in exploration course. So okay, so time to conclude what we have learned. So at this point, we have this complete summary. So we have lambda CDM model, which people believe it's true and describes perfectly well the universe. And all the observations at this point are consistent with the fact that this lambda CDM model has only 6 parameters, which are sort of non-trivial. So contains 6 parameters. And so these are omega b, which is the baryon density, omega of dark matter, cold dark matter. So these are the ratios with respect to the critical density. So if we know these guys now, and then omega lambda. Okay, so these 3 parameters describe basically the history of the homogeneous universe. Okay, so this is the history and matter content of the universe. And whatever, universe. The universe. And basically tell you everything you need to know about the homogeneous universe. Okay? Then you have these extra 2 parameters, which describes your fluctuations, which eventually gave rise to this large-scale structure and so on. So, and you know them, so you say that one of them is the scalar spectral index, and the other one is the amplitude, which I denoted yesterday as A0. So that's the amplitude of prime modular fluctuations, and this is the spectral index for the scale waves. And so these describe the fluctuations. And that last parameter, tau, is this reionization optical depth. And so as I said, so after the recombination, everything was sort of neutral until the first stars actually formed. And you had some supernova explosions and so on. And so you have very high energetic processes, which actually so producing lots of high energetic photons. And these photons actually kicked out the electrons from your neutral plasma. And your plasma get reionized. Okay, so once that happens, you describe how your CMB, which is coming through this ionized plasma, how it is affected. And this is described by this optical depth here. So that's the last parameter. So this is really all there is to know about the universe. And all you need to know is these 6 parameters. And all the observations at this point are consistent with these parameters. So of course, what I'm saying here is that I'm sort of tuning the other parameters to their natural values. So for example, I'm completely neglecting omega k and saying omega k is equal to 0. For example, the curvature omega k is equal to 0. I am saying that, well, if the scale mode is all there is to know, then I'm sort of neglecting the possibility of gravity waves produced by inflation. So what you are, for example, saying is that the ratio which we did here is actually equal to 0, something like that. So R equal to 0 and so on. So you tune the other parameters to their natural values. But it seems that the universe seems to be consistent with the flat universe. It's consistent with the fact that we don't really have gravitational waves produced by the inflation. It's consistent with the fact that really the spectral index is a constant, and then I can characterize all my fluctuations by this amplitude of fluctuations. And so I have like a power law for my fluctuations. And so, yeah. So this is the current picture for the universe. And can I have the screen, please? Maybe, let's see if it works. Oh, thank you so much. But my computer died, so. maybe let's have complete darkness. So we have darkness, but there we go. So here's our universe. And so I tried to describe to you, how this universe looks like. And so we started our description by saying that the universe is actually homogeneous and isotropic. And so basically, if you see the distribution of galaxies, it's all very uniform and nice in large scales. And the truth is you have very only tiny fluctuations of your CMB and so on. So that's what we started with. And then we discussed the fact that it is actually composed mostly by unknown things. So only the baryonic matter, which is 5% of the universe, is actually something which we know about. But then we have this dark matter, which is still not detected. And then we have the dark energy, which we don't know what it is. And so then we discussed the thermal history of the universe and how much helium was formed and how much hydrogen was formed and the recombination and how the CMB was released and how perhaps at the beginning we had inflation, right? And so why the inflation actually postulate is quite interesting. And how many puzzles, classical puzzles of the homogeneous universe it solves, but also that it gives rise to these fluctuations. And so here are your inhomogeneities. So we observe them as CMB, but also we can perhaps observe the gravitational wave coming from inflation, and then CMB coming from us. Of course, if we can observe the gravitational waves, we can look much further to the Big Bang than the CMB, because CMB is just until here, universe is completely non-transparent for the photons, and we cannot observe that. And so here's our current understanding. So basically, you can describe everything by these 6 parameters, which I just described to you. Okay, so to finish, I have a quiz for you. So this is our current understanding of the universe. But let's look at the previous understanding of the universe, and let's look at various theories people had in the past of the universe. And the question is, can you guess which country, which time is actually is that understanding of the universe? So any guesses? So this is like the universe which you observe is a god which is like twisted, and then the stars are actually fit to that god. So any guesses? This is simple. Ancient Egypt, very good. So now this will be difficult. So this is another picture. So let's say Canada. Very good. That's Canada. So that's the Heidi culture. That's the Heidi culture, and the idea is that you had an ocean and raven, and so the raven actually dived into the ocean and brought back some land. And also people in the shell, and that's how our Earth was created and how people started. Okay, so if you are in Canada, just go to Vancouver. It's this beautiful thing. Okay, so here this is probably also simple.
Greek.
Oh.
Very good. So it's Greece, ancient Greece, but also like what is this? People like Israel, countries like Israel, and these close east. Okay, so ancient Greece. So now this one will be also simple.
Indians?
Exactly. So Maya, ancient Maya. And so the last one is very difficult.
That's nice. The squirrel.
So you can see the turtle, the catwin, and then you have carrying the elephants and this squirrel. And of course, there's many turtles like this going through the universe, and they eventually go to some place where they mate. And so this is our current understanding, how people understand our universe in England. And of course, this is due to Terry Pratchett. So anyway, so let's have the lights on. And thank you. And I would like to thank our TA Vasudev and our fellow David for helping me with the course. Okay, now it's not visible, but I wish you, so thank you so much for your attention, and I wish you good luck in your future endeavors.